a little bit on the overview of the topic number 6, compressible flow through nozzles, diffusers, and wind tunnels. So if you are referring to the Anderson book, you need to go into chapter number 10. Okay, so we will cover 6.1, the overview. Even though in Anderson book, they explain a much lengthy introduction on this particular topic, but for the sake of our lecture, we are going to just briefly give an overview of the chapter. And then we will look into the governing equations for quasi-one-dimensional flow, right? So 6.2, hopefully we will finish 6.2 before we have our short break at the middle of our lecture today. And right afterwards, we will then look into nozzle flows. However, with regard to nozzle flows, we are just going to cover the theory behind it. So the examples with regards to the questions on examples for nozzle flow, we have to cover it next week because we would not have enough time to go through all the 5 examples today. So the example, we leave it next week. We just go through the theory on the nozzle flows. All right, that's the plan today, 6.1, 6.2, as well as 6.3. Okay, with regard to the overview of our topic, topic number 6. So basically, as usual, we will use the roadmap for the chapter 6. So this is the roadmap for chapter 6. And what we are going to do is, after we derive the governing equation, we will look at the development of the governing equations for quasi-one-dimensional flow. We will then followed by nozzle flows as well as topic on diffusers, right? So right upon completing nozzle flows and diffusers, of course, nozzle flow will be covered today, but diffusers will be covered next week. Then we will wrap up our session to look into the supersonic wind tunnels aspect. With regard to supersonic wind tunnel, most likely I will share a short video clip on the wind tunnel that are available at University Putra Malaysia in UPM, and also some interesting video clips that you can also find it in YouTube, for example. So examples of experiments being conducted using supersonic wind tunnels. All right. So in this particular chapter, compared to the rest, we will discuss the aerodynamic fundamentals of compressible flow through ducts. All this while, what we have already gone through so far, we are looking at compressible flow above or on an aircraft. It is not through ducts or a confined space. So such fundamentals are vital to the proper design of high-speed wind tunnels. When you are looking at rocket engines, the design of the rocket engines, especially at the nozzle part, right? High energy gas dynamic as well as chemical lasers and jet engines. Those applications of compressible flow through ducts will be highly useful for this kind of applications. So indeed, the material developed in this chapter is used almost daily by practicing aerodynamicists. So basically, the researchers, the scientists, the engineers that are dealing with high-speed aerodynamics, especially for the compressible flow, and they need to use the information that we are going to learn. And it is also indispensable toward a full understanding of compressible flow. All right. So let us go into the 6.2 governing equation for quasi-one-dimensional flow. But before that, if you are interested to know more on the overview, you may want to go to chapter 10 of Anderson book, and you may read through some historical background in terms of how the development of supersonic tunnel, hypersonic tunnel, the rocket engine, especially on the nozzle part. So it is being elaborated in much detail. All right. Okay. When we talk about governing equations for quasi-one-dimensional flow, so in this particular section, the aerodynamics of compressible flow through ducts or internal region will be discussed. So we are talking about flow of high speed into a confined space, into a duct or a tunnel, right? So such fundamentals are vital to the proper design of high-speed wind tunnels, right? Rocket engines, high-energy gas dynamic and chemical lasers, as well as jet engine and others. So for ducted case, the flow is treated as one-dimensional flow, right? So we normally treat it as a one-dimensional flow case. So thus we can consider the flow field variables to be a function in the x direction. So since we are talking about one-dimensional, so it is only considered to be one direction as a function of x only. And that is when we talk about the pressure is in the x direction. When we talk about the velocity, u is also in the x component, and others, etc. So for previous one-dimensional flow, okay, so we have in looking at the earlier aerodynamics one, when you talk about incompressible flow, the area is constant as shown in figure 2. This is figure 2, one-dimensional flow, like a flow in the cylinder, for example, and quasi one-dimensional flow is something shaped like this, like a bottle, right? So in contrast, for this quasi one-dimensional case, in ducted case, the area changes as a function of x. If we look here, one-dimensional flow, the normal one-dimensional flow is that the area remain constant. So the area at the inlet over here, okay, as shown in by my cursor just now, is similar. It is the same as the area at the exit over there, right? So inlet area and exit area are remain constant for one-dimensional flow. However, for quasi one-dimensional flow, the area itself is not constant, right? You can see that the diameter here is smaller than the exit, or the other way around. So what is can be said that the area changes as a function of the x direction. A is also a function of x direction, as sketched in the figure 2b over here, right? All of these components, the area, the pressure, the density, the temperature, the velocity, are also a function of the x direction. All right. So strictly in figure 2b, and this flow is actually three-dimensional, where the velocity at the boundary of the stream, a stream tube, we call this as a stream tube, must be tangent to the boundary, and hence it has components in the y as well as the z direction, okay, as well of course in the x direction itself. So x, y, and z is actually a three-dimensional case. So, however, so if the area variation is moderate, the component in the y and the z, if it is the area variation is moderate, the component in the y and z directions are small compared to the x. There are changes, but we can consider it to be very small compared to the x direction. So in such case, the flow field variables can only be assumed. This is what our assumption. We assume to consider only in the x direction, right? That's the reason. That's why we call it as a quasi one-dimensional flow, even though in real case it is actually three-dimensional, right? So although the assumption of quasi one-dimensional flow is an approximation, because just now we said there are components for y as well as z, but it is small compared to the x direction, to the actual flow in the variable area duct. The integral forms of the conservation equation, namely, we know that there is continuity equation, momentum equation, and energy equation can be used. So we have already introduced this, the continuity, momentum, and energy equation. So they can also be used to obtain the governing equations for this particular quasi one-dimensional flow. All right. Right. Let us look here. And the flow are uniform across any cross-section area, as well as vary only in the x direction, quasi one-dimensional flow. So even, let's say we consider a case here where we have seen this before, right? So we have a convergent divergent nozzle over here, like a duct, right? So for this type of ducted case, consider the control volume. We want to consider a control volume from 1 to 2. We are not going to look at from here to here, from a big area to another big area, but we just consider a control volume from station 1. So this is our station 1, finite control volume for quasi one-dimensional flow. So we have all the parameters, the velocity, the pressure, the temperature, as well as the area at section or station 1. And of course, the flow across area A1 is assumed to be uniform with properties. And these are the properties that I already mentioned just now. Similarly, at station 2, we have a station 2 at the exit of the control volume. So we also have the area. Okay, we have A2, we also have the pressure, the density, and the velocity, as well as, of course, the temperature at the station number 2, like being shown in this figure number 3. All right. So let us go through the derivation for this particular kind of problem for quasi one-dimensional flow. Knowing continuity equation in the form of equation like this expression. So we have this continuity equation. We have the component of the density and velocity with respect to the entropy, as well as the triple integration for the density with the volume, the capital V there, right? So knowing a steady flow condition with time over there, right? So we have this continuity equation for the problem. So use the same method that we have already used before in the derivation. So we then have the at station 1 density time velocity time area, which actually the mass flow rate, m dot equal to rho UA. So at station 1 as well as at station 2, which is then equate to 0. Quasi one-dimensional flow case where V equal to U, right? So simplifying the equation, then we bring the equation on this side, right? So we bring the this U station 1 values to the other side, then we then get this simplified equation for quasi one-dimensional flow. All right. So now we want to consider the momentum equation. Just now is continuity equation. If you look at my slides, the notes that I'm giving you is a simplified version compared to the one being discussed in Anderson, which is a little bit lengthy. So I've already simplified it so that we can easily go to the application, knowing the final equation that need to be used, then we can jump straight into the application later on. So we consider the momentum equation now in the form of this expression, right? And knowing steady flow condition, change in d over dt equal to 0, and f equal to 0, and inviscid flow. So then we have this expression, right? And we know that vector equation, since we assume only in the x direction, then we can rearrange it to be equate as this expression, right? So we then simplify the equation. We have this expression, upper and lower integral, basically representing the station 1 and 2. Area in station 1, area in station 2. And we also know that quasi-one-dimensional flow, one-dimensional case where V equal to U. So we then replace all the U to be equal to V, right? Let us now consider energy equation. So we have continuity, we have already looked at momentum. Now we look at the energy equation in the form of this expression. So similarly, we have the condition over there where the flow is now adiabatic, right? Okay, we then get the expression over here where we have the component of the energy. So rearranging it, and we get this expression as well as this next expression. All right. So we want to divide the equation with continuity equation. So this energy equation, we then divide it with continuity equation where we know that the rho UA at station 1 equal to rho UA at station 2, right? So left hand side and right hand side is this one, all right? So we then divide this term with the continuity equation, right? So the result is that we have a more simplified equation after the energy equation being divided by the continuity equation. From our previous enthalpy equation, we then rearrange it to be more simplified, where we also have the specific volume, which is equal to V equal to 1 over the density, right? So we replace the specific volume, right? And we then have the enthalpy in terms of the pressure and density. So replacing those values in this expression, right? And substitute and rearrange the equation, we then have the expression of enthalpy as well as the velocity at station 1 equal to enthalpy at station 2, okay, as well as the velocity squared at station 2. Knowing that the H naught, right, which is equal to the H plus V squared over 2, then from the equation here, we know that H naught 1 equal to H naught 2, and it proves that H naught is constant throughout the shock wave, where H naught is considered constant. All right. So because of the change in the area, so as we can obviously see here, area at station 1 is smaller than area at station number 2, right? We first need to obtain some differential expressions for the governing equation. So in contrast to the algebraic solution using equations obtained earlier, so using continuity differential expression, so we have this continuity equation, then we know that rho UA is now constant, right? And the small change in rho UA, the density time velocity time the area, will be equal to 0, right? With regard to momentum differential expression, right, just now, continuity differential expression. Now we look at the momentum differential equation. Applying previous momentum equation to the infinitesimal control volume sketched in this figure, right? So basically, the properties at station 1 and with plus for station 2, we have the properties like pressure plus a small change in pressure, area plus a small change in area. So in respect to the x direction, right? So we know from our previous momentum equation, this is the expression. So we then conduct the momentum differential expression. So all product of differential such as dp over dA, the d rho over du squared are very small, right? So those components are very small. Then we make another assumption that they can be ignored, right? And that's the equation. So this equation can then be reduced to an expression given down here, all right? So where we have the area with the small change in pressure plus the area time velocity squared with the small change in the density plus density times the velocity squared with a small change in the area plus the 2 times the density times velocity times the area, okay, with a small change in the velocity, which is equate to 0. All right. Now we want to expand the continuity equation, right? We want to expand the continuity equation where small change in density times velocity times area that we have already shown earlier, which is equal to 0. And we want to multiply by the velocity, right? So we have this d over dx of this component, right? Okay, and we get this expression. Subtracting the equation below, right? Okay, and then we subtract the negative sign. We then obtain this, and finally we obtain an expression of the change in pressure, which is equal to the density times velocity times with respect to the small change in the velocity. This is in this equation, we call it as the Euler equation, right? So we already got the Euler equation for the quasi one-dimensional flow. Next, we want to look at the energy differential expression. So we have already looked at continuity differential expression, momentum differential expression. Now, the turn of energy, energy differential expression. So, looking at this enthalpy expression, right, where we know that the enthalpy plus velocity squared over 2 is constant, differentiating the equation, we get this expression. So in summary, right, so we then now can look into the equations that are differential forms for the continuity, momentum, as well as the energy equation respectively for steady, inviscid, adiabatic, quasi one-dimensional flow. So these are the continuity differential expression, right? The momentum differential expression and the energy differential expression for quasi one-dimensional flow. All right. Let us now use the differential forms of the governing equations that which we obtained in the previous slide to study some physical characteristics of quasi one-dimensional flow, where we need to differentiating the continuity equation, right, which is equal to 0, and then divide it by the mass flow, which is rho time velocity time the area. So we have this, okay, and then we can put the this is the answers, right, where at first we wish to obtain an equation that relates the change in velocity du, right? The change in velocity du to the change in the area itself. Hence, to eliminate the d rho over rho, right, in the equation above, we need to consider momentum equation that can be written as this to be rearranged to get this expression, dp over rho, instead of just dp equal to negative rho u du. All right. So dp over rho is basically we just bring the solving this, where we know that dp over the rho times d rho over rho is exactly actually this expression. All right. And what we can assume is that no shock wave in the flow, where the flow is isentropic, in particular any change in the density, so the small change in the density with respect to the change in pressure dp take place isentropically, that is being written by this equation. From our earlier speed of sound equation, we know A is our speed of sound. So there's a change of pressure over the change in density equal to the speed of sound squared, right? Substituting this equation into the equation below, so we then get a new expression with regards to the speed of sound, right? We want to rearrange the equation that we have already obtained just now, and we have this expression, right? So now we can see that there is a component of Mach number, okay? Substituting this equation into earlier equation, we then have this expression where we now have the Mach number. Rearranging this equation, we can now get a small change in the area over the area will be equal to the Mach number squared minus 1 times the change in velocity over the value of the velocity. So this equation relates to the change in area to change in velocity, which is called the area velocity relation, and very important to this study. All right. So this is the expression from the equation. A positive value of du, this change in velocity, notes an increase in velocity, right? So when we see a positive value of du, meaning that there will be increase in velocity. When there is a negative value of du, we note that there will be a decrease in velocity. All right. So with this equation, that tell us the following information. So for a range of Mach number from 0 to 1, 0 equal or less than 1, which we consider it as subsonic flow. So the quantity in the parenthesis, okay, in the equation is negative, right? So we look over here. If it is less than 1, meaning that anything less than 1, you will have a negative value, means that there will be a decrease in the velocity. All right. So hence an increase in the velocity associated with the decrease in the area. All right. So likewise, a decrease in the velocity is associated with an increase in the area, positive dA. All right. So clearly, for subsonic compressible flow, to increase the velocity, we must have a convergent duct instead of a divergent duct, because we can see that the area itself, if you have a negative value on this side, meaning that you have a higher area. Okay, higher area lead to the less velocity. Small area lead to the higher velocity, right? So to increase velocity, we must have a convergent duct. And to decrease the velocity, we must have a divergent duct. So this is converge, okay, where velocity is increasing from a large area to a small area. So this is happening for Mach number less than 1, right? But when the flow is flowing from a small area to the large area, so the velocity decrease, right? So we have a bigger area at the exit, right? So this is for cases of subsonic where Mach number is equal to 0 or less than 1. All right. Let us look at another case here for Mach number more than 1 for supersonic flow. So the quantity in the parenthesis, right, in equation is positive because Mach number is more than 1, right? For imagine this one, Mach number will be if it is more than 1, right? So this value will be positive, right? Okay, so hence what happened is that an increase in velocity, okay, positive du is associated with increase in area, right? So this is aligned with the equation. Likewise, a decrease in velocity associated with a decrease in area. For supersonic flow, where Mach number is more than 1, to increase the velocity, we must have a divergent duct. So if you are designing the intake for an aircraft for supersonic flow, you want to increase the area, increase the velocity, you must increase the area. We must have a divergent duct like this. And to increase the velocity, we must have a convergent duct, right? If you want to decrease the velocity, you have a convergent duct. So they are the direct opposite of the trend for subsonic flow, right? The third case, for in the case of Mach number equal to 1, where we have a sonic flow, right? So the equation itself shows that dA will be equal to 0. Even though a finite du exists, mathematically this corresponds to a local maximum or minimum in the area distribution. Physically, it corresponds to the minimum area as discussed over here. So you can see that in the throat area where Mach number equal to 1, right, that is the minimum area for the duct. If we want subsonic to supersonic speed, then we need to first accelerate the gas subsonically in a convergent duct. So you accelerate the duct to a convergent duct, and then, however, as soon as sonic condition achieved where Mach number equal to 1, we must further expand the gas to supersonic speed by having a divergent duct, convergent divergent duct as shown here, right? So right, in the next case is that if we want to have a supersonic to subsonic speed, right? Now we want from supersonic to subsonic speed more than 1, Mach more than 1 to Mach less than 1. Then we must first decelerate the gas. We have to slow down the gas into a convergent duct, and then as soon as it goes into the throat, right, where Mach number equal to 1, we then further decelerate it to subsonic speed in a divergent duct. This is what we call it as diffuser. All right. So it is two condition over there. Right. With that, I believe it's about time for us to have a short break before we continue on the nozzle topic, right? Because I don't think that better we have a break now before we continue on the nozzle flow